chapter, we will be discussing a more convenient way of representing where the electrons are located in the various atoms. The quantum numbers are essentially a zip code telling us where we can find various kinds of electrons, but this zip code is not really very easily understood, so therefore we would like to come up with a simplified approach to doing that. Electron configurations are a shorthand way of representing the distribution of electrons within the atom into the various shells and subshells. Shown here are some examples of the electron configurations of the so-called noble gases. These are situations that are so-called closed shells. The various shells are completely filled with electrons and represent the most stable electron configurations for atoms on the periodic table. If you take a look at the electron configuration for helium, the one to the left of the letter is the principal quantum number for the lowest energy orbital. It corresponds to an L value, which is 1, which is an S-type orbital, and then we have a superscript to the right, which is telling us how many electrons are in there. So the number of electrons for helium is the same as the number of protons in the nucleus, and the atomic number for helium is 2. If you have neon, that's atomic number 10. You'll notice if you add together all of the superscripted numbers, that has to equal the number of electrons, and that should be 10. Likewise for argon, there should be 18, and krypton should be 36. In addition to electron configurations, it's also useful to be able to relate them to the so-called orbital diagrams. Orbital diagrams are a shorthand way of representing Bohr's energy diagrams. And so as an example, if we had an atom such as fluorine having the electron configuration shown here, fluorine has a total of 9 electrons, so if you were to take and add together the superscripts to the right of each of the letters, that would give you a total of 9. The various electrons that can go into the subshells, the S can never hold more than 2 electrons. So the 1s has 2 electrons, likewise the 2s has 2 electrons. But since the P has 3 orbitals, each orbital, the px, the py, and the bz, can hold up to 2 electrons. And so in this case, it could hold a total of 6 electrons. In the case of fluorine, there are only 5 electrons in that orbital. So we could then represent our so-called energy diagram from the Bohr model. We represent each of the possible orbitals at a particular energy, the lowest energy being the 1s. There is a circle there representing the shape of the orbital, and so the 2s is higher than that. The 2p is slightly higher than the 2s, but they are both in the same shell. There happens to be 3 of those p orbitals, the px, the py, and the pz orbital. It turns out we can put our electrons in representing their spin in terms of arrows. The up arrow is the spin ms value of +1/2. The down arrow is the spin down arrow. Turns out that if we have opposite spins, that is an energetically reasonable way to put 2 similarly charged electrons in relatively close proximity to one another. We can also then put 2 more electrons into the 2s orbital, and then we have the remaining 5 electrons that go into the p-type orbitals. So it turns out that the p orbitals are all at pretty much the same energy. We refer to these as being degenerate type orbitals. Degeneracy means having essentially equal energies. Now, the shorthand way of representing the orbital diagram is to write the relative energy of the orbitals from left to right. So the lowest energy orbital, the 1s, is the furthest to the left. The next orbital is the 2s. Then the remaining 2p orbitals are grouped together, placing the number and letter designations underneath each of the groupings. Just as a reminder of how Bohr organized his energy diagrams, he originally started out saying that all of the electrons in a particular shell occurred at the same energy, so therefore the subshells were at the same energy. Subsequently, to explain the complexity of the emission spectra for the multi-electron elements, came to realize this was not a very good description. As a result, a better description of the complexity of the emission spectra was arrived at by realizing that the various subshells did not occur at the same energy, but there was the relative ordering of within the shells, the relative ordering of the subshells meant that always the S for a particular shell was lower in energy than the P, which would be lower in energy than the D, and so on and so forth. This is represented in the energy diagram that you see here, and from this we can then start to come up with our shorthand ways of representing the electron configurations and the orbital diagrams. As I indicated earlier, when we put two electrons within the same orbital, the arrows have to be pointed in opposite directions. This represents two electrons that have the opposite spin quantum numbers of +1/2 and -1/2. The Pauli exclusion principle is a way of accounting for that in terms of the quantum numbers, and Pauli made the statement that it is not possible for two electrons within the same atom to have all four quantum numbers being exactly the same. It is possible to have three of the quantum numbers be the same. So, for example, in helium, you can have both of the electrons have a principal quantum number of 1. This would be both electrons in the n=1 shell, and the next value, the letter designation would be S, so both electrons would be in the s orbital, and the m sub l value would be 0, and they both would be in an m sub l value, but the thing that has to then be different is that the two spins have to be different. So one of the spins would have to be +1/2 and the other would have to be -1/2. So this is a way that we can represent our electron configuration then, but to be more specific in terms of how you can represent your spins, if both of the arrows are pointing up, that's implying that the m sub s values for both of those electrons is +1/2, and that violates the Pauli exclusion principle. So, for one of those electrons, here's your 4 quantum numbers, but the second electron, if it has all 4 of the spin, or all 4 of the quantum numbers the same, that's not allowed. So, if we then do it so that the electrons have opposite spin, then that is something that is allowed by the Pauli exclusion principle. This table will help us remember how many possible electrons can go into each of the subshells. This is related to the m sub L values for each of these subshells. So it turns out that for any particular shell, there's always an S-type orbital with an L value of 0. There is only one m sub L possible value, therefore there's only one what we refer to as an orbital. And any one orbital can hold up to 2 electrons. Both of those electrons have to have opposite spins. It turns out that a p-type orbital, which has an L value of 1, has 3 possible m sub L values, -1, 0, and +1. And that represents the 3 different p orbitals, the px, the py, and the pz. Each one of those orbitals can hold up to 2 electrons, and therefore a p subshell can hold up to 6 electrons. The d subshell, when we get to the n equals 3 shell, it's possible to have d orbitals. The L value for d is 2. That means there are 5 different m sub L values. There's -2, -1, 0, +1, and +2. Each could hold up to 2 electrons for a total of 10 possible electrons. If we continue this pattern, you'll notice that in each of the letter designations, the number of orbitals has increased by 2. So therefore the F, there are 7 F-type orbitals with a maximum of 14 electrons. This in fact corresponds very well with the organization of the periodic table. This then brings us to the so-called building up principle, which is a way of figuring out how to put electrons into the various shells and subshells. This is sometimes referred to as the Aufbau principle, which is German. The word Aufbau means building up. And so we will use the rules to describe the so-called ground state electron configurations. The ground state, of course, is the lowest energy situation for each of the elements. So the first rule is that we can't violate the Pauli exclusion principle. No 2 electrons in an atom can have the same 4 quantum numbers. Therefore, no 2 electrons in a particular orbital can have the same m sub s values. It turns out then that we fill the subshells in the order that you see here. This is roughly the ordering that occurs in terms of energy, taking into account the splitting of the various subshells and the possibility that there is some overlap. You can either go ahead and memorize this order, or we will talk about the energy diagram in terms of the Aufbau principle in just a moment.